14 too, it was just asked like kind of what we do this year. So first term is chapters 12, 13, 14, and then second term is 15, 16 final exam. That's it. So chapter 14 is a pretty big chapter. I used to split it into two halves and test on the two halves separately. Normandale's already on section 14.7. They're kind of like, they emphasize that to me this week, but we get several more weeks than they do. Like, we get a lot more time than they do, and they started earlier. So they're on a different schedule than we are. But anyway, so we're behind them, but we're not behind in general. Like, I have the calendar planned out for the whole term, and we're fine. We're right on track. So no worries. We will finish the whole thing by the end of the term, unless like some unforeseen craziness happens. But chapter 14, just so you know what chapter 14 is, chapter 14 focuses on derivatives and applications of derivatives for multivariable functions. So remember with derivatives, so obviously we have motion, but we also have tangent lines, right? Slopes of tangent lines, and all the applications associated with slopes of tangent lines, which when we talk about multivariable functions, we talk about this thing called the gradient that we'll get into. So on Monday and Tuesday, we will our first step into what are called partial derivatives, which are really fun. So if they're simple, they're easier to level. So we'll be doing partial derivatives. We'll learn chain rule with partial derivatives, right? We have all these new little things. The other applications that come with derivatives, of course, are maxes and mins, right? So we'll be doing relative extrema, we'll be doing absolute extrema, right? That kind of stuff. So that's chapter 14. Chapter 15 is integrals and applications of integrals with multivariable functions. One of the biggest focuses of chapter 15 is volume. So we'll be doing volume of really crazy spaces. Last year, with traditional calculus, you could do a volume by revolution, or a volume with something that had a consistent cross-section. Now you're going to be able to find a volume of anything. Like anything in the world, if you can map it, you can find the volume. So anyway, and that's where we do what are called multiple integrals or iterated integrals. When you have if you've ever seen like double and triple integrals with the integral symbol right next to each other, right? They're easier than you think. Everything looks scary, and then when you do it, you're like, yeah, it's really not that bad. Okay. So anyway, so that's chapter 15, right? And then the very final chapter focuses on what are called line integrals, which is essentially we go back to vector valued functions, because if you remember, the graph of a vector valued function isn't a surface, it's like a curve through space. I think of it like a wire, right? Like if you were to take like a wire through space, right? Some sort of a curve that goes through space. That's the graph of the vector valued function. Well, with line integrals, what you can do with that then is do things like hang a curtain from that line and find the area of the curtain, right? Like kind of fun, different things. We'll also do a lot of things with flow. There's problems with water flow and air flow and stuff like that. There's a lot of physics in chapter 16. So anyway, yeah, but that's what we've got coming up. Right now, we're just starting chapter 14. Today's lesson is pretty simple. It's just limits and continuity of multivariable functions. So for our warm-up, use a 3D grapher to look at the graph of e to the 1/2 xy and then sketch a level curve. Look, you guys have no idea how awesome this is. You will not hear me go ugh anymore on my recordings, right? Because I can now use my scroll bar. All right. So I'm just going to do a shout out. Thank you, Miss McSherry, for fixing my laptop for me. Okay. So let's just take a look. Okay. I think every single one of you, yeah, they all look beautiful. So when you were doing your level curves, one way to do it was just to plug in the number. This is one way, but honestly, the easiest way, if you pick, let's just pick like e squared. If you have e to the 1/2 xy equals e squared, then 1/2 xy equals 2. And so then you get y equals 4 over x, right? And you just solve each one for y and sketch the graph. And then you get the level curves. Did anyone actually graph the actual function? Yes? Can you picture what it looks like if you didn't graph it? Let's see, e to the 1/2 xy. We'll graph it real quick. And then we'll move on. I did tell you to graph it, but I don't know if you guys, like, how much do you actually listen to me? So, let's see. Choose e to the Whoa, look at that. Kind of fun, right? Does it kind of make sense that if you were to slice this off, like level curve, so Ryan, you weren't here, but just so you know, a level curve is where if you were to slice this graph, this 3D graph, with a horizontal plane, right? So say, here, let's just add an equation. So say we graphed the equation z equals e squared. Well, that's too high. Let me zoom out. There we go. Then what the level curve is it's like the curve of intersection of those two things, right? And then if you were to graph z equals e, what was another one we had? E to the 1/2, e to the 1/2, right? Same thing, curve of intersection, that's called the level curve. And what happens is when you graph all the level curves, you create what's called a contour map, which is how we get maps like topological maps of like mountain ranges that are flat. You say, where do the mountains equal 1,000 feet? Where do they equal 2,000 feet, right? You slice them all off, you flatten them down and graph them on a plane, and you get your contour map, right? That's what level curves are. They're the creation of a contour map. It's kind of, I don't know why, I just love Grapher. I just have so much fun spinning these graphs around. All right. Okay. All right, so today, 14.2, I even changed the chapter number. Limits with multiple variables. I can understand the concept of limits for a function of two variables. There's part of this that's super easy, and part of this that's a little tricky. So we'll walk through it, and hopefully by the end of the day, you'll feel comfortable with everything. All right. Okay, limits. So when we did two-dimensional limits, the limit was the y value that the function was approaching as x approached an x value. Well, now, so that was like, here's the thing. So when we have some function, right? So if you have some x value, as you zeroed in, like homed in on that x value, what y value, the closer you got to that x value from each side, what y value were you getting closer and closer to, right? And so the limit is the y value that as x gets closer to some value, y gets closer to some value. That's called the limit. Okay. So in 3 dimensions, what happens is since our input is 2 variables, you create, instead of like this, you create this circle that goes around the spot. So like your x, you have an ordered pair for your input, your x and y. And so how do you decide if you're going this way or this way? You don't. You kind of close in around it. And then whatever z value comes out, the closer you create, like the closer that circle gets around the point, does your z value close in on one spot, right? That's the conceptual version of the limit. So the limit, so think of the limit as the z value of a function that the function approaches as a circle of space closes in around some ordered pair. if you need to show, this is the part that is tricky. If you need to show that a limit does not exist, you can show this by approaching the limit from two different paths and showing the limits are not the same. Now, the tricky thing about knowing if, do you remember back in the old days when we did limits, 0 over 0 meant the limit exists, keep going, right? Now, in any other number over 0, the limit doesn't exist, you're just done. Same thing here. If you get something not 0 over 0, it still does not exist, you're done, you don't even have to do anything else because life is easy. But when you get 0 over 0, that is questionable. So if we're trying to find the limit as x approaches, or as x comma y approaches the point 1, 1 on the graph of x minus 1 over y minus 1, so when we plug in our 1, 1, 1 for x, 1 for y, we get 0 over 0. So then we have to kind of do some stabbing at this. And so there's a couple different strategies to see if you can figure out how to show that the limit doesn't exist. And I've got so I'm going to walk you kind of through different ways to approach the limit. So as we approach, okay, so 1, 1. So just pretend we're on an old-fashioned xy plane. So we're approaching this point, right? We can approach this point from any direction we want, right? No matter which direction we come from, as long as we're approaching this point, we better get the same z value out. Because if we don't, then the limit doesn't exist. Does that make sense? Yes, kind of? Okay, I know it's hot. Do you think it's hot?
Yes.
Okay, good. All right. Whew. All right. So anyway, so the first thing I'm going to show you is instead of doing the point x equals 1, y equals 1, if we do the order pair x comma x approaches 1, 1. So this kind of, it feels weird, but it's where you're letting you're on the line y equals x. So instead of approaching from like here, you're actually approaching that way. So if we approach where we let our y be x and we let x approach 1, 1, and you change your y to x and you plug in a 1. So now what happens? We can use traditional limits, which means when you have a traditional limit, you can cancel common factors and you get a limit of 1. I know this feels weird. Does it feel weird?
Yeah.
Okay, that's okay. Just stay with me. Stay with me, okay?
How can you change the variable?
Okay, so so here's the thing. We're still approaching the same spot, right? We're still approaching the same spot. But we're gonna approach it from different directions. So so here are your options. You either let your y become x and approach it from x comma x. You let your x become y, approach it from y comma y. Or we could plug in a constant. Here, I'll let you see. Okay. So this would approach 1, 1 from, I even did it right here. I didn't even notice that. From the road y equals x. So we're kind of coming along that way. All right. So suppose instead of changing instead of doing it from y, because if we did it from y, we'd get the exact same thing. We'd still have 1, right? So let's try something different. What if we let x be a constant of 1, and then your y stays y, right? So if your x is a constant of 1, now you're approaching it from this way. You're on the line x equals 1. Here you are on the line y equals x. Now you're on the line x equals 1. So if you let your x be a constant and put y to y, then you plug in a 1 for x, you get 0 over y minus 1. I know this is really weird, but you are allowed to say 0 over y minus 1 equals 0. It doesn't feel, that one never really feels right to me, but that's accepted. So I know that's really weird, but if you have constant it's not like you're approaching. It's not like this is a variable that's approaching 0 over 0. This is a hard 0. Like there's no changing it. This is a hard 0 over numbers approaching 0. So a hard 0 over numbers approaching 0, you get to keep it at 0. So I know it's really weird, but anyway, so you end up with a limit of 1 and a limit of 0. And as soon as you get two limits that don't match, then your limit doesn't exist. So here's what I put. So I wrote this last year. So sorry, the easiest ones that for you to find are the ones where you get your limit to equal 1 and then you get your limit to equal 0. And so really what you want to do is think about what I found is change my x to y or my y to x, or make my x a constant or my y a constant. Those are your like 4 roads that are easiest to travel down, where you can usually get it to spit out 2 different answers, depending on your 2 different roads. Okay, let's try a couple more, because that's like our first intro step into this. Just so you know, most limits are really easy. So we're going to do some that are like 2 seconds. So for example, like let's just, you know what, I'm going to cover this.
I can go back to the last one.
I can. And then I'm going to add a rectangle so that we don't work ahead. You okay? Are we good? Okay. All right. Don't go ahead. Wait, I'm going to add a rectangle so you can't see. Paint. There we go. Okay. All right, so we're going to work these one at a time. We'll work them together because they don't take that long. All right, so for our first one, we have the limit as xy approaches the point 2, 1 on the graph of x plus 3y squared. Do you think this will ever be DNE? No, it's never going to be undefined. It's always going to exist. Go ahead and if you have one that you think where the graph is just continuous, you could just plug in the point and get the limit. Jack, you got 5?
I did get 5.
Did you get 5? All right. Hey, I got 5. Good. 1 for 1. All right. Any questions on that one?
Oh, shoot the long way. What? Yeah, please.
There is no long way. Are you?
I confused something else.
Are you thinking of finding a derivative of the definition? Okay. All right. All right, try this one. That happens to me too. What is shocking me more is that you're wearing a winter coat.
No, it's cold outside today, but it was really hot outside.
Do not
It's hot in here. Like you are welcome to
Do
take it off.
not have any.
Take it off. Take it off.
But there's you have like extra layers on as well.
The thing is, that's visually pleasing though.
Oh.
Visually pleasing. The red and the white look very well together. It's a cartoon character. That's just like a.
It's just a coat.
It's a coat. You know, there's no style, no flavor.
All right. So, what you guys get?
Well, root 2 over 2.
Sai, what'd you get?
Root 2 over 2.
Okay, yeah, you guys are like above and beyond. I just put 1 over root 2.
Signs are good.
Good. Any questions? That one you can just plug in. If you plug in, you get an answer. That's probably right. All right. This one, where would we have a problem with this one? If it was approaching 0, 0, right? Then we'd have a problem. Okay. Whoa. Whoops. Okay. All right, next one. Suppose xy approaches the point pi fourths comma 2 on the function y times the cosine of xy. Vikram, how are you doing? Are you? What'd you get for this one? 0? That's what I got. Well done. All right. Any questions on that? We're kind of going through these a little bit quick. Okay. We're good? All right. Whoa, 3 variables. Okay. So the limit as x, y, z approaches the ordered triple 2, 0, 1 on the graph x e to the y z. Just plug in the point. It's no different. All right, Amal, what'd you get? 2. Anyone else get 2? Everyone? Well done. All right. Okay. This one's actually easy.
You don't have to do that weird.
Yeah, you don't have to do the weird thing. You need 0 to 0. Yeah. Oh.
Yeah, so it's just
Nick, what'd you get for this one? D and E? Why D and E? Good. What if it was 0 dividing by 0? Wouldn't be D and E then. What makes it D and E? Okay, because it's a not 0 over 0. So yes, you can just say it's D. All right. Yeah, when you get 0 over 0, that's do you remember last year we learned the word indeterminate, right? 0 over 0 is an indeterminate limit. Not 0 over 0 is not indeterminate, it's just D and E and you're done. So, all right. I think I have one more. Yeah. Aha! Your favorite. All right, so this is the one that's going to actually put the rubber to the road. So see if you can figure out how to show that, well, either if this limit does exist or if it doesn't exist. To show a limit does exist that approaches 0 over 0 is like almost impossible. But to show that it doesn't exist is actually pretty easy. You just need to find, I don't know. Because, well, like there's no way to show every path, right? And there's infinitely many, so I don't know.
Can you just say it doesn't
Yeah. So. Give them all a pass and do what? Only one path? But the whole point, like the whole definition of limit is that you have to be able to approach it from all sides. So, yeah. There's always infinite limit paths for any limit.
So we did limit as x.
Oh no, it's your.
Just use your big.
Yeah,
brain.
That's one
I think you're
over
in
two.
the past when
So,
X and Y are the same number.
One,
And then this would be the same.
Like if X is 1 and Y is 2,
one
and
over
you're
one
substituting
plus
like
y. And then
You'd still be able to change it. If you had x comma y approach equal to 1 comma 2, you could make x a constant of 1 or y a constant of 2, or you could figure out an equation that got you to that point
so equals 1, right?
and like substitute y for whatever that equation is.
I said a constant.
So, yeah.
Oh, I thought. Yeah.
Wait, what?
Wait, Mrs. Price?
Yes.
So if you said like x equals to a constant, can it be any? I'm not putting any number.
Well, it still has to approach the same point. Yeah, you have to always be approaching the point 0, 0.
So like, so we said x equals to 0 then.
You put x equal to a hard constant of 0,
Yeah.
so you get 0 over y, which is 0. So you got one of them.
And I got one half of that.
If you set x, y for x.
Yeah.
There you go.
Oh, so you can't just pick a random number to set x equals to.
No, it has to approach the same point.
So it has to approach 0.
Yes.
Well, like in the coordinates underneath.
Delete this. Lily, how are you?
I'm good. I'm ready to do it.
Really? Did you find any paths?
Well, it would go through zeros, like, if X is equal to 0,
One.
Y is equal to 0.
Okay. So could you try? I'm not going to look and see. All right, who can give Lily a hand and give her an idea of a slightly different limit that approaches the same point?
Because like if you said x equals 0, you get 0
Yeah, right.
x 0 and x
X comma x approaches 0 comma 0. So now you're approaching that point, but you're approaching it from the line y equals x, so you're approaching it from the diagonal. Well, let's watch what happens. So we change our x, or our y to x, so you get the limit, rewrite your limit. You know I'm going to take off for notation. Okay, so we have x over x plus x. And now you can cancel an x top and bottom, right? And you end up, when you cancel an x top and bottom, you just end up with a half. Is that okay? Okay.
So you could do, if it's like 0, if you use 0 as your constant and it's 0 over
It's 0. Yes. I know. That's the part that's the hardest for me to accept. But that's what I have seen in like every single place that I've looked, which isn't a lot, but it's not a lot, but it's not none. So every time I get stuck on a concept, so my first place to go is your book. My second place is always on Paul's online math notes. Did I ever talk about Paul's online math notes? Yeah, I love Paul's online math notes. Yeah. So that's my second go-to. If I'm still stuck and I've tried the Larson book and the Stewart book and Paul's online math notes, then I go to the MIT open source stuff and I read that. So, but they all say this is okay. So I go with it because they're every one of those sources is smarter than I am. All right. So then, okay. What was the other one that you guys chose then? 0 comma y. So you let x be just a hard constant of 0. So now you're approaching point 0, 0 from this way, like vertically. From so x is just always 0. So what you end up with then is the limit as 0 comma y approaches 0 comma 0 of, and you get 0 over y, which is 0. And as soon as you get two different things, so I did it different when I did it. There's multiple ways to skin this cat, right? So I let y go to 0. It's an expression. It's not something I want to do. I let y go to 0, be a hard constant of 0, and if you let set y equal to be a hard constant of 0 where you're approaching horizontally, then you get the limit of x over x, which is 1. Yes?
So for the second limit, you changed it to 0y. Does it have to be 0 because it approaches 0, 0? Or
Yes.
Okay.
Yeah, it has to approach the point.
Okay. So
Yeah, if you set it to like 5y, it wouldn't make any sense.
Okay.
Yeah. Good. Other questions? All right, so that's pretty much as hard as it gets as in limit world. And that's all. That's it. That's